Welcome to part 3 of the video on definite integrals. In this third video on definite integrals, we're going to talk about some basic properties of definite integrals. The first of these properties is a property that we already saw with indefinite integrals. That is, when you have a definite integral of a function and you have a constant here, you can take the constant out of the integral sign. That is, you can calculate this integral as 3 times the integral of the other function. So this is just like indefinite integrals. You can do this also with definite integrals. The second property is also something that we already saw in indefinite integrals. That is, if you have the sum of two functions, you can calculate the integral of the sum of the integrals of each of the functions. So the integral of sum equals the sum of the integrals. So these are just basic properties that definite integrals have in common with indefinite integrals. So you can do algebraically anything that you can do with indefinite integrals, you can do with definite integrals. So now, another important property of definite integrals is the mean value theorem. We already studied the mean value theorem for derivatives, and there is a similar theorem for integrals. And let's take a function like this one here. Let's say that this is the graph of function f of x. Let's take 2 points a and b, like this. And we saw in the previous videos that the definite integrals gives us this area, the area under the curve. That is, if we take the integral from a to b of this function, this is by definition this area. So now, what the mean value theorem says that if you start taking rectangles like this one, if you take this rectangle of base equals to this segment, that is b minus a, and you keep increasing the height like this, you will reach a point at which the area of this rectangle will equal the area under the curve. There will be a point at which these two areas will be the same. That is, the area of this rectangle equals the area under the curve. And this is pretty intuitive because you just need to keep increasing until you reach the point at which you have the same area. For example, here in this rectangle we don't have this little region here, but we have this region to compensate. So this is pretty intuitive. And we need to write the formulas for this theorem. And to do that, we need to calculate what is the area of this rectangle. The area is base times height. Well, we know what is the base. The base is this segment that equals b minus a. Now, to calculate the height, let's take this point in which the rectangle intersects the function here. And let's say that the x-coordinate of this point is x0. So the y-coordinate will be f of x0 because this is a point in the graph of the function. So the area f of x0 is also the height of this rectangle. So the area of the rectangle is height, that is f of x0, times base, that is b minus a. And what the mean value, and we said that we consider this rectangle such that its area equals the area under the curve. That is the integral from a to b of f of x dx. So now, specifically, what the mean value theorem says that if you take this integral, there will be a point x0 between a and b such that this equality holds. That is, the area of the rectangle with height f of x0 will equal the area under the curve. That is, you can use this equality for a point x0 between a and b. And you can see why this is called the mean value theorem, because it talks about the existence of a point x0 between a and b. So this is a very important property of integrals that will be essential for proving the fundamental theorem of calculus. That will be the subject of the next lesson. So that's all for now. Thank you for watching and see you next time.